To illustrate the application of the 3SLS model, we will consider the Klein Model 1, which we also used in the 2SLS tutorial. This model was introduced by Lawrence R. Klein in 1950. The Klein Model 1 consists of 6 equations and 6 endogenous variables. These endogenous variables are consumption, investment, income, wages, corporate profits, and capital. The exogenous variables in the model include government expenditure, government wage bill, trend, and taxes. In addition to these, we also have some predetermined variables including the lag of corporate profits and the lag of capital stock. We call them predetermined because, in any time period t, we know the values of variables in time t-1 or previous time period. The last 3 equations shown here are the identity equations. These equations don't need to be estimated as they do not contain any parameters. We will estimate the first 3 equations and the parameters of this Klein Model 1 using 3SLS. The first equation shown here is the consumption equation. Consumption is a function of corporate profits, lag of corporate profits, and total wages, including both private and government wage bill. In this equation, total wages and corporate profits are endogenous variables on the right-hand side, and these are related to the error term mu1. We cannot use OLS to estimate this equation due to endogeneity. The second equation of investment contains one endogenous variable, corporate profits, which is related to the error term mu2, causing endogeneity. The other variables, lag of capital and lag of corporate profits, are predetermined variables. Finally, the equation for private wages also contains one endogenous variable, causing endogeneity. This equation also has an exogenous variable, trend, and a predetermined variable. Since 3SLS is a systems method, we will estimate all the 3 equations simultaneously using 3SLS. In R, we can use the system fit function provided in the system fit package to estimate the 3SLS model. Moreover, we can also use this function to estimate 2SLS or OLS models. We will use the same data used by Klein to estimate this model. The data consists of 22 annual observations from 1920 to 1941 in the United States. This data contains all the variables that we need to estimate the Klein Model 1 and is available within the system fit package in R. To estimate this model, we have to first define all the equations and exogenous variables. First, let us define the consumption equation of the Klein Model 1. We know that consumption is the dependent variable and corporate profits, lag of corporate profits, and total wages are the independent variables in the first equation. Therefore, we mention consumption as the dependent variable in the command here, followed by the independent variables. Second, we define the investment equation in a similar manner. Here, investment is the dependent variable and corporate profits, lag of corporate profits, and lag of capital are independent variables in the second equation of Klein Model 1. In the third equation of Klein Model 1, private wages is the dependent variable, whereas gross national product, lag of gross national product, and trend are the independent variables as mentioned here. Now that we have defined the 3 equations to be estimated, we must mention all the exogenous and predetermined variables in the Klein Model 1. These variables will be used as instruments in the first stage to obtain the predicted values of endogenous variables. By specifying these instruments, the software will know that the remaining variables in the equations are endogenous variables. Next, we can create a list object of all the equations in Klein Model 1. In the command shown here, we have included all the 3 equations of Klein Model 1 that we have to estimate using 3SLS. We have named this list as Klein Model. Finally, we can apply the system fit function to estimate 3SLS. In the system fit command shown here, Klein Model is our list object which contains all the equations that we defined earlier. With this, the function knows the structure of all our equations. The 3SLS option tells the function to estimate a 3SLS model. Here, we can also specify 2SLS to estimate all equations one by one using 2SLS approach. We can specify OLS to apply the ordinary least squares model. The inst option is used to specify all the exogenous and predetermined variables that will be used as instruments in the first stage. We have mentioned the instruments object here, which we defined earlier. The option data is equal to z tells the function which dataset to use to estimate the 3 SLS coefficients. This function will automatically take care of all the stages of 3 SLS and report the results of the final stage and 3 SLS coefficients. Stata provides the reg3 command to estimate the 3 SLS model. In addition to 3 SLS, we can also estimate the 2 SLS and OLS models using this reg3 command. In fact, we can specify and estimate all equations of the model in a single command. The command shown here will estimate all the 3 equations of Klein Model 1. First, we define all the equations of the model within this command. The first equation here specifies consumption as the dependent variable and corporate profits, lag of corporate profits and total wages as independent variables. Within the next brackets, we have defined the second equation of investment. Here, investment is the dependent variable, whereas corporate profits, lag of corporate profits and lag of capital are independent variables. We define the third equation of Klein Model 1 in a similar manner, with private wages as dependent variable and GNP, lag of GNP and trend as independent variables. Finally, we have to specify all the exogenous and predetermined variables in the model. This way, the function will know which variables are exogenous and all the remaining variables are endogenous. Our Klein model has 7 exogenous and predetermined variables as mentioned here, and these will be used as instruments in the first stage. The option 3 SLS in the end will estimate these equations using the 3 SLS approach. Here, we can specify 2 SLS for 2-stage least squares and OLS to estimate using ordinary least squares. This command will automatically estimate all the stages of 3 SLS and report the results of the final stage and 3 SLS coefficients. When we estimate the 3 SLS model, the results of all the equations are reported together because they are estimated simultaneously. The results report all the usual statistics, including the coefficients, standard errors, t and p-values. As an example, let us take a look at the results of the consumption equation of Klein Model 1. In the table shown here, we can clearly see that only the coefficient of total wages is statistically significant, and there is a positive relationship between total wages and consumption. With an increase in wages, consumption will increase. The coefficients of corporate profits and lag of corporate profits are not statistically significant. The interpretation of all these coefficients is similar to how we interpret the 2 SLS and OLS coefficients. If we compare the results of 3 SLS with OLS and 2 SLS coefficients, we can see some clear differences between the results. The constant and the coefficient of total wages are similar in all the models. But the coefficients of corporate profits and lag of corporate profits and their statistical significance are different. If the total wages and corporate profits variables are truly endogenous, we know that OLS estimates will be biased and inconsistent here. Due to the bias, OLS is overestimating the coefficient of corporate profits and showing it to be statistically significant. On the other hand, 2 SLS and 3 SLS results show that this coefficient is insignificant as they correct for endogeneity and bias. The lag of corporate profits and its coefficient is significant at 10% level in 2 SLS results, whereas it is insignificant in 3 SLS. There is only a minor difference between the coefficient estimated by 2 SLS and 3 SLS. However, if the equations are correctly specified, we know that the 3 SLS coefficient will be more efficient and precise. In addition to the results of the equations, some programs also report the variance-covariance matrix of residuals that was used in the estimation of the 3 SLS model. For instance, the variance-covariance matrix from stage 2, which was used in estimating this Klein Model 1, is shown here. You can see that this is a 3 by 3 matrix because we are estimating 3 equations of consumption, investment, and private wages. The results of the investment and private wages equations are reported in the same way as the consumption equation. We can also interpret and compare their results with two SLS and OLS models in the same way. We must be very careful when applying the 3SLS model since it estimates the system simultaneously. If the error terms of different equations are not related to each other, then the 3SLS model simply reduces to a 2SLS model. The 2SLS model is automatically preferred if the error terms are not correlated. Next, the error terms of the equations must not be autocorrelated. If they are autocorrelated, the results of 3SLS model are not reliable. Finally, the coefficients of 3SLS model are more efficient than 2SLS coefficients only if the structure and equations of the model are correctly specified. Even if one of the equations is misspecified, the 3SLS coefficients will be biased and inconsistent. Suppose one equation is misspecified when estimating the 3SLS model. Remember, we have to obtain the variance-covariance matrix of residuals in stage 2, which acts as the weight matrix in stage 3 of 3SLS. The residuals of this misspecified equation will affect this entire weight matrix when the variance and covariances are estimated. Therefore, when the variables are transformed in stage 3, the misspecification will be transferred to all the equations and their coefficients. As a result, the coefficients will end up being not only biased but also inconsistent. On the other hand, 2SLS is a single equation approach. So, misspecification in one equation will not affect the other equations because they are estimated separately and one by one. Therefore, if an equation is misspecified, 2SLS results will be better as compared to 3SLS. Similarly, the 2SLS model should be preferred if we are only interested in one equation which has some endogenous variables and we don't know the structure of the other equations of the model. This is because 3SLS requires all equations to be correctly specified and the results will be biased and inconsistent if any equation is misspecified. The Hausman Specification test can give us some indication of whether 3SLS equations have been misspecified. Using this test, we can compare the 2SLS and 3SLS results to check how different their coefficients are. If the equations are correctly specified, then 2SLS and 3SLS coefficients will not be too different because both methods are consistent. However, 3SLS estimates will be more efficient than 2SLS. On the other hand, if 2SLS and 3SLS coefficients are far apart, it can indicate that there is some misspecification in the equations. This is because all the 3SLS coefficients will end up biased and inconsistent, whereas 2SLS coefficients will still be consistent. Therefore, under the null hypothesis of this Hausman test, both 2SLS and 3SLS models are consistent while 3SLS is more efficient. Under the alternate hypothesis, only 2SLS model is consistent while the 3SLS is inconsistent. We can apply this Hausman specification test using the system fit package in R. In the command shown here, we have to first mention the object containing our 2SLS model results because it will be consistent under null and the alternate hypothesis. Next, we will mention the object containing 3SLS results, which will be more efficient under the null hypothesis and inconsistent under the alternate hypothesis. In Stata, we can use the Hausman command to apply this test. Again, we mention the stored results of the consistent estimator of 2SLS first. Then, we mention the stored results of the 3SLS model, which will be more efficient under null hypothesis and inconsistent under the alternate hypothesis. The important thing to note here is that we have to store the results of 2SLS and 3SLS models after estimation. When we apply this test to our example of Klein Model 1, we get the results shown here. The first element is the estimated Hausman statistic. The degrees of freedom are 12 because our model estimated 12 coefficients including constants in the three equations. The p-value is 0.8156, which means that we cannot reject the null hypothesis. This means that our 3SLS model should be consistent and more efficient than the 2SLS model, and there is no evidence to suggest that the equations are misspecified. Thank you for watching, and I will see you in the next tutorial.